Well, hello everyone, and welcome to lecture 11 of our Calculus 1 summer course. So today we are going to revisit the general historical context of calculus in light of what we now know, and also going to try to think about what bearing does what we've learned in these last weeks. What bearings it have on our common sense or our orientation in the world? That's a thought to keep in mind as we discuss this from a more high level and historical view, and I'll also touch on a few things you can expect in future calculus classes if you continue on, which will tie naturally into our historical conceptual discussion. So, one question that can often be asked, which almost inevitably has to be asked with any sort of new idea, is it really new? And this happens with all sorts of ideas, with calculus, with Newton and Leibniz, or with famously, I mean, I'm sure we all know Einstein invented relativity, but of course, did he really invent? Was it really new, or was it all already there beforehand? Pretty much any idea you can see, if you look carefully enough at the history, you can come to think, well, this was already here. What did they really invent? But then there's always something really important. I think usually the advent of a new idea is associated with a changed paradigm that naturally creates a natural foundation that frees the concepts to a certain extent to flourish in a more natural fashion, as opposed to having to be discussed in a way that's somewhat of a strained way of speaking about it. But indeed, we can certainly go pretty far back in history and find precursors, very significant precursors to calculus, going back pretty far, and really all across the globe, really. But going back, at least a millennium before. But first, I would like to discuss a couple of what could possibly be seen as impediments to the ideas of calculus, or possibly, obstacles. So, some of you may have heard of Zeno's paradox. So, Zeno's paradox is often stated in terms of Achilles and a tortoise. So Achilles is racing a tortoise, and of course Achilles is a hero, and he can run very quickly, and a tortoise cannot run very quickly. But Achilles gives a head start to the tortoise in the race, and so presumably it's just a matter of time before Achilles catches up with and overtakes the tortoise. But the paradox says, well, okay, so assume Achilles is going to catch up to the tortoise. Well, before he can catch up to the tortoise, he has to get halfway there. And then now he's here. But still, before he can get from this new halfway point, before he can get there to where the tortoise is, he has to get halfway there. And then from here, he's going to have to get halfway, and there halfway, and you can just keep dividing this. So every time he's going to have to get halfway from where he stands at a given time to halfway between there and where the tortoise is. And so each of these halfway points is some task he has to accomplish. He has to get halfway from here, and then halfway from here, and then halfway from here, and halfway from here, and halfway from here. And it's an infinite number of tasks he has to accomplish before he can get there. And Zeno says that you can't complete an infinite number of tasks in a finite amount of time, therefore he can never get there. And Zeno, actually building on the assertions of an earlier gentleman named Parmenides, concludes that motion is actually impossible. It's illusory. Senses are deceiving us. There's no such a thing as motion. And so, of course, you can see some similarity to calculus, and we'll revisit this. You can see some similarity to the concept of a limit. How this really seems to be in opposition to the idea of a limit to a certain extent, or to preclude the concept of a limit. But then another important step along the way, which actually was to a certain extent out of a commentary on Parmenides and Zeno, was Aristotle's contribution, which Aristotle concluded that there was no such a thing as instantaneous velocity, which of course instantaneous velocity is sort of the essence of calculus. If you have x equals f of t, then f prime of t, or we could even just call it x prime of t, just f prime of t, we could call it x prime of t. This is the instantaneous velocity. And I belabored this a bit in the first lecture, this idea of an instantaneous velocity, that you're driving your car, and in some instant you can think of there being, that we all think of there being some speed that we're going at a given instant, as opposed to having to be over a length of time. There's the belabored example in the first lecture, but normally a velocity would be you go a certain distance in a certain time, you take the ratio of those things, you divide them. So, but of course in calculus we have this idea of the instantaneous velocity. And of course it didn't take until Newton for anyone to consider the possibility of instantaneous velocity. Aristotle considered the possibility and concluded that it was not possible. And his conclusion was based on the following reasoning, which is very logical, as most Aristotle's reasoning is, but oftentimes seems quite out of touch with our more modern ways of thinking. But so here's his logic. So every object is either in motion or it's at rest. And the only way that an object can be both in motion and at rest is for it to be in motion at one time and at rest at another time. It can't be in motion at rest and at rest at the same time, because of the law of non-contradiction, because it would be a contradiction. Being in motion contradicts being at rest, so you can't be in motion and at rest. And so the question is, if there is instantaneous velocity, he says, an object, if there was instantaneous velocity, suppose there is instantaneous velocity, then every object has an instantaneous velocity. So say that you push something, like say this eraser, it's currently at rest, now I'm putting it in motion. So it's moving from being at rest to in motion. So, and you could say, well, maybe it has some instantaneous velocity at some point, right? And of course we could, like I just wrote, we could write its length along this chalkboard as a function x of t. Say x equals 0 is right here on this corner, and then x of t, the position of this eraser would be given by x of t, and then we could take its derivative, and that would be the instant velocity. And from what I'm doing, it might be like a sinusoidal function or something. But so what Aristotle says is suppose that there is an instantaneous velocity, which of course in this class we say there is one, but he says suppose that there is an instantaneous velocity, then consider the moment when an object, the instant when an object goes from being at rest to in motion. So if there is an instantaneous velocity, then at that instant where it changes from being at rest to in motion, it has to be either at rest or in motion, right? Because if instantaneous velocity can be defined, there must be some fact of the matter as to whether the object is in motion or at rest at the moment that it switches from one to the other. because of the law of the excluded middle. It can't be not at motion and not at rest. It can't be a third option. It has to be one or the other. The law, you can look up the law of the excluded middle, but that's basically what it says, is that things have to be one way or the other. Something can't be something other than true or false. It has to be true or it has to be false. It can't be, there isn't a third option. So an object has to be at rest or in motion. So then he says, suppose that the object is at rest at the moment that it goes from being at rest and motion. Well, that's a contradiction, because if it was at rest, it wouldn't begin to move. So it can't be at rest at the moment that it goes from being at rest and motion. So, okay, well, that leaves us with the possibility that it's in motion. Well, that can't be right, because if it's in motion, then it wouldn't have been at rest. It would be in motion. So this seems like just a mess. I mean, how can you deal with this? And the way that Aristotle dealt with it is he said there is no such thing as instantaneous velocity. Instantaneous velocity requires an interval of time. Velocity, there's no instantaneous velocity. Velocity requires an interval of time in order for it to be defined, which of course ties into our discussion in the first lecture. And if we graph a function x of t, so this is the x-axis, and this is the t-axis, then say we have this position function. So again, like if this was, I'll do it from this direction. If this right here, say this is x equals 0, then sorry, t should start at 0. Say this is x equals 0, this is x equals 1. So say x equals 1 is like right here. So the eraser is right here. And then it's going to be decreasing closer to 0. Then it's going to come back up. And it's going to come down over here to 0. And then behind 0. Okay? So the velocity, what he's proposing is that in order to define the velocity, we have to pick a point right here, say, and a point right here, and we have to take this position minus this position, take the distance between the two, which is going to be the rise in this graph, and then divide it by the time between the two, the time interval between the two, which is the run in this graph. Divide the two, so of course that's the slope of the secant line. And the way I've drawn this graph, it looks kind of like pretty close to tangent line, but you could imagine the graph would be more curved. So basically what he's asserting in terms of our calculus terminology is he's asserting that there's no such a thing as the tangent line, there's only the secant line, and there couldn't be the tangent line. Which of course, stated in those words, it seems sort of bizarre. It seems wrong. And of course, sometimes there actually isn't a tangent line. Like if you consider the function absolute value of x, but since we're dealing with time, let's say x equals the absolute value of t minus 1. So that's going to be a function that's like this. So there legitimately is no tangent line right here. Because the tangent line is like this, and then it's like this. I mean, you could say there's no tangent line, or there's a whole spectrum of tangent lines in between. But I briefly touched on this earlier, several lectures ago, but the function is not differentiable at this point, because the slope of the tangent line wants to be this, but also wants to be this. But that's really not the crux of the matter with Aristotle's contention. I mean, Aristotle's contention applies even with functions that are perfectly differentiable. Like, for example, we could define a piecewise function that's x equals 0 when t is less than 1, and x equals t minus 1 squared when t is greater than or equal to 1. So that is going to look something like this. You can see here the tangent is horizontal, and so the velocity is defined, and we're still in Aristotle's situation where it's going from being at rest to being in motion. And we could answer his question actually by saying that at this point it's at rest because the velocity is 0. Of course, is it really at rest? I mean, it's about to start moving. So it doesn't really answer the question necessarily. It's easy to laugh at and to look down on Aristotle for a lot of things. A lot of the arguments he made seem cheesy and easy to laugh at, but I think there really is something there that can be kind of like, with this argument, I think there's something to what he's saying that is a little bit unsettling and not necessarily answered as much as ignored by our whole approach here with calculus. But anyways, so speaking of tangent lines, so I mentioned that with this absolute value type situation, that we don't have a tangent line right here. So what exactly defines a tangent line? Of course, in this class we've really spoken mostly of the tangent line in terms of the derivative, but people spoke about tangent lines long before they spoke about derivatives. And the first mentions of tangent lines, I think the first ones that are really known are from Euclid. Antiphon, who was 5th century BC, briefly mentioned. Antiphon mentioned method of exhaustion, which I'll get to in a second. But Euclid, I think I could be wrong about this actually, but Euclid certainly did mention tangent lines, but there may have been earlier references. I'm not sure if Antiphon mentioned them. But Euclid, anyways, 4th century BC, wrote the Elements, the famous well, it's a series of textbooks really on, or you could call it a several volume textbook on mathematics that was like the main authority on mathematics for an incredibly long time. But so the way that Euclid defined tangent lines is he defined it in terms of a circle. He would say it's a line that touches this, that intersects with the circle only at a single point. So of course, if you think about it, this must be the same as the tangent line in the sense we've been using this class, because any line that intersects it at multiple points is going to be a secant line, and any line that doesn't intersect it is certainly not going to be a tangent line. And this is also adequate for ellipses, but it's not adequate in general, because like for a parabola, at the vertex, you could put a vertical line at the vertex that clearly is not a tangent in the sense that we're interested in, but it only intersects this parabola at this one point. And of course, the tangent also satisfies that. But this definition is not good enough in the case of the parabola, because now there are multiple lines that intersect only at one point. And so the definition of the tangent was slightly improved by Apollonius, who sharpened the idea slightly, but then in his studies of conic sections, because parabolas and hyperbolas are also conic sections, and so he sharpened the idea a little bit in the context of conic sections. But the really remarkable definition of it came from Archimedes, who was considering what is now known as Archimedes' spiral. And how Archimedes defined the tangent line was, if you have a curve, if you have a point that's moving along a curve, then what direction is it moving at a given time? So like right here, it's moving this way. So this is really a definition of the tangent line that is very modern. And Archimedes, so Archimedes of Syracuse was also 3rd century BC, I believe, and he was quite ahead of his time in some ways. He was killed by a Roman soldier. They were invading Sicily, but I mean, we can imagine that mathematics, that many of the developments we have now would have developed back then if that hadn't happened. I mean, who knows? We can imagine. But so he has this definition that really is quite remarkable, and it combines. It really. I mean, if you think about it, like with this spiral, this tangent is going to be intersecting with this curve all over the place, so he's not relying on these sort of clumsy special cases like the circle that were being relied on with Euclid. And nothing in Europe would come close to surpassing Archimedes, or really even matching Archimedes oftentimes, but definitely surpassing Archimedes for quite a long time. Like I said, I think the next, after Archimedes, the next major, as far as I know, the next major advancement in mathematics in the whole Mediterranean region would have been the development of algebra in Baghdad that I talked about in lecture 6. So things went dormant in Europe for a while, but of course a parallel to the development of the concept of the tangent is something called the method of exhaustion, which is seen as the precursor to integration, and indeed is quite fair to be regarded as such. And this method of exhaustion has to do with taking polygons, or these more straightened figures that can be reasoned about more easily, and doing something that essentially amounts kind of like to taking a limit of getting closer and closer to the curved figure like the circle. A curved figure like the circle. And Archimedes was able to use this method to demonstrate the fact that we know now about the relationship between the area and the circumference of a circle. So we know that the circumference is 2 pi r, and the area is pi r squared. And of course, we've sort of artificially introduced pi into the equation because, I mean, we know what pi is now, but pi is a ratio that's defined in terms of these quantities. This is really maybe more naturally expressed, is saying that C equals A times 2 divided by R. So 2AR, C equals 2AR. She was able to prove using this method of exhaustion. Also, Euclid used this method of exhaustion, which of course I'm not carefully defining a method of exhaustion, I hope you don't mind, but it has to do with this approximating these curved situations with straight situations. Euclid also used this method of exhaustion in the elements to derive formulas for the volume of a cone and the volume of a cylinder and various things like that are conceivably doable without modern day calculus, although they're much easier with modern day calculus. So that's method of exhaustion. So method of exhaustion was being used by Euclid in 5th century BC and in Greece, and then by Archimedes in Sicily, but also, so this was all 3rd, 4th century BC, but then it was independently popped back up in China in the 3rd century. A gentleman named Lee Hugh developed the same idea, the method of exhaustion to compute certain areas and volumes. And so what's the next thing I want to talk about in this historical development? So going back to India and the Nila school, so I talked before about Madhava, but before Madhava, long before Madhava, there was a gentleman named, and hopefully I'm going to pronounce this right, Aryabhata, 6th century AD. And Aryabhata was considering very small segments of arcs of a circle, very small arcs of a circle, and the ratios. He was considering very small arcs of a circle and their ratios to the chords cutting them. So if you don't remember what a chord is it's a straight line that sort of like a secant line, but you just consider it as subtending. They call it subtending the arc. So you don't extend it out here, you just consider it to be subtending the arc. And so he was considering very small chords. So that's sort of a big chord. You can consider a small chord. You can consider a much smaller chord. But he considered these small chords and the relationship between the small chord and the arc. And so if you think about this, if you make the arc arbitrarily small, then the arc and the chord will ultimately be identical, and the chord will ultimately, if we consider it as a secant line extended outwards, it'll ultimately become the tangent line. And so Aryabhata talked about this idea, and he said some things that, according to a scholar who wrote a historical paper on this that I was looking at, I think the Indian History of Science Society or something, but he was saying that it's actually somewhat unclear exactly what Aryabhata was saying, but whether he was I think as students and instructor in Calculus 1 course, we can all relate to this. People are not sure. I guess it's somewhat ambiguous as to whether he was talking about a specific example or a general principle. But it seems that what he was suggesting is that as the arc gets quite small, it comes to coincide with the chord, which of course would very much be along the lines of calculus and the idea of the tangent line in terms of this infinite vanishing quantity, which would really be a huge innovation and a huge step towards the modern notion of calculus, because that's something, that notion of the point approaching closer to the other point, that's totally absent in even Archimedes and the more advanced ideas of the tangent in the Mediterranean. They didn't come close to this idea of the points getting close. In fact, no one really came to that idea again until Newton, basically, or at least close to Newton. So 17th century. So that would be a very big development, but it's somewhat ambiguous as to whether he's talking about a case of a 24 or 96 sided figure, or if he's actually talking about diminishing it infinitely small. And so he also used, some of you may know you may have learned this in high school or middle school geometry. You may or may not have learned that if you take the radius of the circle and with a compass and straight edge, you can divide the circle into a hexagon. You can naturally get so you divide the circle into 6 angles, and then you can divide that. You can always cut these in half, and 6 times 2 times 2 times 2 times 2 is 96. So he divided the circle into 96 parts. The 96 at first, and he divided this up, and then divided this up, and then you kept going. He divided it into 96 parts, and he made a big table of sine values that would have, okay, here's the angle, here's the sine of the thing. So like in your unit circle that you learned in trigonometry class, you just have like pi over 3, pi over 6, pi over 2, and then pi over 4, and these other things. So he had 96 different things. He had a table of 96 different values. And apparently some people took this a little bit literally and took some of his comments literally, or maybe took them in what we can now see in the history of ideas as the wrong direction. And specifically, a gentleman who came about a generation after Aryabhata, a gentleman named Bhaskara. So Bhaskara came to a conclusion that, in retrospect, seems very strange. So granted, Bhaskara made some mathematical advances in the field of number theory, which is the study of whole numbers, but the whole idea of continuity seems to have not been his forte. So here's what he said. He said, "It is proper to say that a unit arc can be equal to its chord." And so in other words, what he's saying is not only is the secant line close to the circle, it actually is the circle. It says, but we say an arc equal to a chord exists. So he's saying that if you make this arc small enough, not only does it get close to being the curve, it actually is the same as the curve. He says, but we say an arc equal to a chord exists. If an arc could not be equal to a chord, then there would never be steadiness at all for an iron ball. Therefore, we infer that there is some spot by means of which that iron ball rests on level ground, and that spot is the 96th part of the circumference. So what he's saying is basically, and this of course, this also has a little bit of an intuitive appeal. So if you think about it, a wheel, or in his case, an iron ball, how can it rest on a single point? There must be some flatness down here that it's able to rest on. If there was all a single point, it wouldn't be stable. So there must be flatness. So essentially, assuming that the translation of assuming that he's been correctly understood, which it seems pretty unambiguous, essentially what he's asserting is that there's no such a thing as a circle. There's just that what we think is a circle is actually a 96-sided figure. It's a 96-sided figure. And this, of course, not 96 sides, but you get the point. So it rests on something flat, and it's a 96-sided figure with flat sides. And, of course, this number 96, the number 96 was used by Aryabhata. It was used by, he made 96 subdivisions of the circle for his sine table. It was used, actually, interestingly, it was also used by Archimedes in providing estimates, upper and lower bounds on what pi must be. So there might be some historical context to why people are obsessed with 96 that we haven't fully been able to keep track of. But yeah, so anyway, so he came to this conclusion that could also be seen as, so on the one hand we have Aristotle, and we can see Aristotle's thinking as being somewhat stifling, or possibly, closing the floodgates of what could have flown in as calculus. Who knows? Maybe not. But we can also perhaps see the same thing in Bhaskara. But so it really appears that insofar as the development of these geometric ideas towards calculus, that it really ended with Archimedes, and more or less ended with Archimedes in the Mediterranean, and then more or less ended with Aryabhata in India. But then, of course, I mentioned before, Madhava in the 14th century is the next what I could trace to be the next significant development in Indian mathematics. And of course, he went back to considering infinitely. So you could say that he went back to Aryabhata, but then of course, deepened it by considering, if you take an infinitely, zooming into the circle, take an infinitely small arc and chord of the circle and consider their relationship to each other, and that you can get an increasing degree of precision. And then Madhava and his school developed a lot of sophisticated ideas in order to actually be able to give a power series relationship expressing the angle, or what we can now call the arc length along the circle, expressing it in terms of the slope of a given line. So relating slope and angle, of course, you can imagine is important. He was able to do that giving a power series. So speaking of that, so I said I was going to tie in what comes next if you continue on in the calculus curriculum. And one thing that comes next is something called a power series that I touched on maybe a little bit in one of the previous lectures. I can't remember what lecture number it was, but the idea of a power series really comes from these higher order approximations. So, recall I said that f of x is f of x0 is approximately equal, f of x for x near x0 is approximately equal to f of x0 plus f prime of x0 times x minus x0. So this is the linear approximation, and then the second order approximation, 1/2 second derivative of x0 times x minus x0 squared. And then if we want to make this even more precise, we do plus 1/6 third derivative x0 times third derivative of f applied at x0 times x minus x0 cubed. This is always approximate. We're making the approximation better and better, but it's always approximate. As opposed to, for it to be an infinite series, you could just say, get rid of the approximate, say exactly equal, but then we're just going to keep going and going, so we're never going to terminate. It's just going to keep going and going. So we're going to be summing together more and more stuff. So 1 over 24, because 24 is 4 times 6, recall 6 is 2 times 3. That's why we get this here. We have to cancel out this thing, if you remember what I was talking about. If not, it's not important. I'm just sort of giving a high-level sketch. But then 24 fourth derivative, and then we could x minus x0 to the fourth power. And then we could have these little dots to indicate that it just keeps going and going and going. So we are no longer talking about approximate, we're talking about exact, because we're indicating that it just keeps going and going and going and going. And in fact, Madhava, or actually, I don't think Madhava actually articulated this as much as a student of Madhava's a generation or so later, whose name is slipping me. But I think Madhava just laid the groundwork of this, and these things are maybe attributed to him, but there's no record of him actually having written them. But soon after, and still well before Newton and Cavalieri and all the developments in Europe. But what the Madhava and the Kerala school derived was that arctangent, the power series of arctangent of x, power series of arctangent of x, which is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9, and then minus x to the 11 over 11 plus minus and plus minus plus minus plus, going on and on and on. Of course, we have an equality here because we're saying that we're going to infinity. And then I introduced the sum notation earlier, and I'm just going to write this so that when you see it, you can say, next year if you take Cop T, you can say, oh, I've seen that before, but you could write this in terms of the sum notation, n equals 1 to infinity x -1, the n minus 1 over, or times, all this times, I'll write it all in numerator, -1, n minus 1 times x to the n over 2n plus 1, sorry, 2n minus 1, so we're just adding up all these things. So when this is 1, this is just going to be x, and when it is 3, this is going to be minus x cubed over 3, and it's going to go on. You can just take my word for it that this in this notation, this expresses the same thing. If you want, you can pause and think for a second about why this with the dot 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 notation is the same as this. And normally, remember, when we did the sums with the integrals, there was something on the top, but now we have infinity on the top of the sum, so we're just adding it together an infinite number of terms. So this is the power series idea, which is often attributed to Newton or his contemporaries, but it was really present in the writings of people in the Kerala school and Madhava's followers. But of course, the way that they wrote it, and this I think applies to Newton to some extent as well, but the way that they wrote about this was all in verse. They didn't have equations like this, so it would be like so in this case with arctangent, the tangent is going to be like some quantity that would be expressed as a slope or a height of a triangle. Probably would be described as the height of a triangle. Recall you can have tangent is the height of a triangle with base 1, height tangent theta, and hypotenuse secant theta. And so I don't recall how exactly Madhava describes x, but he would talk about that quantity. So like, say for example here, so in terms of the language of arctangent, so if x is tangent, and of course this would be square root of 1 plus x squared. But so he would speak of, say, this is the height of the triangle, say the height of the triangle, and then so removed from the height of the triangle would be the cube of the height of the triangle divided by 3, or in more wordy language than that even. I wish I had an exact quote to read you, but it's like this language that's like very like descriptive and like prose, like you're just reading a book. There's like no formulas or anything. So it's very interesting. And it's interesting to read Newton, because even Newton's writings are sort of more like that. I mean, there are geometric figures, but there aren't any, at least the Principia Mathematica, there are geometric figures, but there aren't any formulas. So everything, all these concepts, with Newton, it's really all the concepts that we're talking about in this class, but they're developed in a fashion that doesn't involve writing any formulas, which is very interesting to see. Okay, so Madhava, 14th century. So then the next, as far as I could trace things, the next major development after Madhava was Cavalieri. Cavalieri, of course, was not too long before Newton. He was the early 17th century, and Cavalieri put forward what we call Cavalieri's principle. He proposed the idea that if you have some sort of area, that you can regard this area as being made up by an infinite number of lines, and that if you shift these lines around, it doesn't change the area. So if we move everything up or down, it doesn't change the area. Of course, I've given you a few problems that relate to this over the course of this class. And in fact, one of the extra credit problems relates to this. Let's see if I have them out so I can tell you which one it is. I don't. But one of the extra credit problems does relate to this, and maybe you'll be able to detect which one it is. It's one of the latter ones that it's like it's asking for the area within a parametric shape. But anyway, so Cavalieri's principle And you can think of it as like if you have a row of toothpicks, you can rearrange those toothpicks, and the total area of the row of toothpicks doesn't change. Or I don't know if any of you are smokers, hopefully not, but like if you took some cigarettes and you laid them out, or chalk, pieces of chalk. So these pieces of chalk right here, you can think of this two-dimensional figure formed by these pieces of chalk, and I can rearrange and move these pieces of chalk around however I want. I see that very well. I can move these pieces of chalk around however I want, and the area of the figure made up by them is always going to be the same. It's not going to change just by me rearranging, moving some up and some down. The area is always going to be the same, and that's what I still don't know actually how well you can see that. That the area of this figure is always going to be the same, no matter how we rearrange these things relative to each other. So now it's sort of a funny shaped figure. Now it's closer to like a diamond. Again, sort of a funny shaped figure. But no matter how we rearrange this figure, it's always going to have the same area. We can imagine that instead of those pieces of chalk that actually have some width, we can imagine that it's these infinitely small lines, and we can move them around, but the area stays the same. So in some sense, you could almost read the fundamental theorem of calculus into this idea, because you can see that you have an area, and that area being divided into infinitely many lines. You could say, like, well, right here, the area is if you were to extend the shape further, the area would be growing by adding little lines to it. So that's sort of like the fundamental theorem of calculus. You can see the fundamental theorem of calculus if you want it. I mean, clearly he didn't state the fundamental theorem of calculus. Now, okay, so Cavalieri's principle was heavily criticized, and what exactly are the reasons it was criticized for? Of course, I think I mentioned in lecture 1 that there's some argument about what the reasons were they motivated by considerations other than the uninterested pursuit of truth. Maybe not, but certainly there were legitimate logical issues with what he was putting forward, and one in particular that was raised was the question of a cone. So with a cone, like a party hat or whatever, if you think about it, you could try to apply the same principle to circles. So say you have a circle, or you have a disc, and you divide it into a bunch of little circles. You think, okay, great, now it must be the case that, and to put it in terms of party hats, that say I have a party hat that fits on my head. So the circumference of the base of the party hat is the same. So you should be able to just pull these circles out and not affect the surface area of the party hat, right? The cone. So you should be able to just pull these out, and the surface area will always be the same, you might think, from Cavalieri's principle, because it's just, the cone is just made up of a whole bunch of little circles. And of course that is not legitimate. So you think about the surface of a flat disc. Say there's a flat disc with the circumference of my head. The surface area of that is going to be much smaller than, say, I'm wearing a party hat that's like 2 feet tall on top of my head, but has the correct circumference of my head. If you just think about it intuitively, clearly the surface area of that party hat is going to be orders of magnitude bigger than the surface area of the disc that has the same circumference as my head. So that's basically was considered to be the most intense criticism of his works, which happened to be by a mathematician who's a Jesuit. So of course, some people read some motives into it that this was some sort of policing of some idea that was dangerous for theological reasons, but whether or not there's any truth to that, there were certainly logical, mathematical objections that a perfectly reasonable person with no ulterior motives could easily make. But so if you think about this, it's sort of like a telescope. But if you think about a telescope, when you expand out a telescope, when something telescopes, there are also, it's not just circles or cylinders, and there's more surface coming from the sides of the cylinder, the exterior of the cylinder, right? The cylinder has more surface, not just a circle. So if you were to just pull out all the circles and just consider these circles, if you were to look at the telescope from the side, if you ignored that, you would have a whole bunch of empty spaces. So that's really where pieces are missing, and why the surface area of the big party hat is not the same as the surface area of the little hat. You can think of it as imagining it like a conical slinky. If you were to pull out a conical slinky, there would be all of these slices that would be missing if you could look at it from the side. If you looked at it from the top, it might look like it was the same surface area, right? This might be a top view of it, but from the side, it would clearly be missing. It would clearly be missing a ton. Or if we thought of it in terms of the telescope, it would be missing a ton. There would be lots of empty spaces. Now, exactly what the empty spaces would look like, how many of them there would be, well, that's really a deep conundrum, given that there's an infinite number of these circles going on, or an infinite number of lines in Cavalieri's principles. So you can imagine why lots of questions were raised about this idea. So then, Cavalieri was in some sense, revolutionary in the history of ideas and bringing forth calculus, but then also in some sense was somewhat of a false start, one could say. But so then, the next big development really, some ideas from that point were beginning to develop towards calculus. But then, of course, the next really big development was the invention of calculus as we know it today with Newton and Leibniz. And of course, so with Leibniz, there was more of a notion of the infinitely small, that you're not taking a limit, you're actually getting there. So like Leibniz would say that x squared equals, x equals x0 plus dx. So they're, infinitely close to each other. They're like adjacent points on the curve. It's like you imagine this curve being made up of a couple points. x0 and x are next to each other. So then x would be x0 plus dx squared, which would equal FOIL method, x0 squared plus 2x0 dx plus dx squared. And then Leibniz said, well, dx is so small that dx squared disappears, but dx is still there. And so, of course, it seems a little bit sketchy. But he talked about it in a way that maybe seems precise, but still more precise than I'm making it sound with this sort of caricature, but still leaves something to be desired. And so Newton endeavored to put calculus on a footing that was based in geometry and reminiscent of Euclid, because everyone still trusted Euclid to that time. Euclid was considered like the gold standard of rigor at that point in time. Of course, now people have their own different ideas as to what's rigorous, and Euclid's considered very much yesteryear in terms of standards of rigor. But at the time, Euclid was considered the gold standard of rigor. So with first Leibniz published his version of calculus, and Newton said, "How dare you? I shared my private correspondence with you, and now you're publishing it and pretending it's your own." And so then Newton endeavored to publish everything and endeavored to put it on a geometric footing with the Principia The first 11 propositions of the Principia are beautiful. I'm going to attach them in this lecture so you can look at them. They're absolutely beautiful. He puts it all into a geometric footing that modern mathematicians will look back on and say that it's lacking in various ways and it's not sufficiently rigorous, and people attribute the idea of a limit to Cauchy, and they say that Newton didn't really have the idea of a limit. I personally, and having spent some time looking at the Principia, I think that he's not given enough credit. I think Newton deserves more credit than he gets for really. He basically did state the idea of a limit, and I'm not completely alone in saying that he probably deserves more credit. I mean, I've read commentaries that say the same thing, but I might even be more radical in thinking how much credit he deserves. But if you look at Lemma 1, for example, Lemma 1 says, quantities and the ratios of quantities, which in any finite time converge continually to equality, and before the end of that time approach nearer the one to the other than by any given difference, become ultimately equal. So, what's interesting is he's stating it as a lemma rather than as a definition. And his proof of it, he says, if you deny it, suppose them to be ultimately unequal, and let D be their ultimate difference, therefore they cannot approach nearer to equality than by that given difference D, which is against the supposition. So this proof is somewhat classical. It's somewhat similar to the types of things that would be said to justify the method of exhaustion. But it's really, and that was, of course, his point, was to put everything on a more classically well appreciated, well accepted formulation. And but of course, contemporary mathematics seeks to axiomatize everything, which personally I'm very sympathetic to this older style of things where Newton is trying to make statements about some inferring things from some given reality about how geometry works and a given reality of geometric facts, whereas modern mathematicians don't really like to do that. They like to create axioms so that they're not saying anything other than things that are reformulations of their own axioms. I don't know, maybe this is sort of an excessively abstract conversation that may have become meaningless to you already a few minutes ago, but the point is that if you look at Newton's Principia and then you open a modern textbook on real analysis, is the word that's used for rigorous calculus. So if you open a modern day textbook on real analysis, so real analysis gives the rigorous logical foundations of what's considered to be the fully proof-based approach to calculus, proving everything as you go along. If you open a modern day textbook on real analysis and you open the Principia, you'll notice extreme differences in paradigm, and I'm just saying that I think that the Principia, and the way that he proceeds in the Principia, is noticeably ambiguous, and it might be seemingly ambiguous. It requires quite a bit of meditation and thought on the part of the reader, which of course I kind of think is cool, and so I posted it on here so you can take a look at it. Of course, Lemma 2, Lemma 4, some of these early lemmas relate to the areas under the curve and the rectangles that we've been talking about in the previous lecture, and that you talked about in recitation. So then Lemma 6 is very interesting, because in Lemma 6 what he's essentially saying, and it took me a while to decode this because his language is so different than the language we use now, but what he's essentially proving in Lemma 6 is that the tangent line is the angle between the tangent line to a curve and the curve itself, that angle is 0. So it's sort of interesting. It sort of made me scratch my head a little bit as what definition is he using of a tangent line, because he's assuming something about what a tangent line is and then using it in his proof so that's, in modern mathematical training, it's like, okay, you're going to prove something about a tangent line. Well, how are you defining a tangent line? We've talked a little bit about how various people have defined tangent lines, and I'm not actually satisfied that I know exactly how he's defining a tangent line. But either way, he proves, or I guess who knows whether it's a proof or a statement necessarily, that the angle between the tangent line and the curve is 0, which is a very good characterization of the tangent line. Of course, in modern mathematics, that would be a tautology. You'd say, what's the angle between a line and a curve? It's the angle between the tangent line and the line. But anyways, he gives this as he gives it as a property of the tangent line, that it has angle 0 with the curve. And the way he does it is sort of interesting. He says that, okay, so assume that the curve, he says that you have the tangent line, and assume that the curvature is continued, he puts it, which means that this curve is continued. So assume that the angle that it made with the tangent line was not 0. So the angle it made with the tangent line was not 0, then he says the curvature could not be continued. And making a non-zero angle, if the curve were to be continued, it would have to cut right through the tangent line. And so he's saying that it wouldn't be a tangent line if the curve cut right through it. And what this could be is a definition of the tangent line that was in usage as late as the 19th century, so a while after Newton, was that the tangent line is a line that touches the curve but does not cross it. A line that touches the curve but does not cross it. And I'm going to actually leave that as your homework assignment, to say what's wrong with this definition. But there's something wrong with this definition, and it's something that we talked about in lecture, whatever the lecture was, where we talked about second derivatives and maxes and mins and inflection points and all these things. But, so the claim is that, so I'll write out the statement of exactly what I'm asking for. So what is wrong with the following 19th century definition of the tangent line? So, and then here's the definition. Tangent line to a curve at a point x0 is the line that intersects the curve at x0, but does not cross the curve. Of course, we could draw a number of pictures that would make this definition very compelling, like with say this curve. So anywhere we go on this curve, the tangent line is going to be exactly the line that is touching at one point and not crossing the curve. But what I'm asking you to find is some reason or some curve where this definition is not adequate, where a tangent line does not meet this definition. And like I said, whatever the lecture was where we talked about second derivatives, I think it was lecture 4 or lecture 5, where we talked about second derivatives, we talked about critical points, we talked about inflection points. So what is it that corresponds to what is it that causes this definition not to work? So, have a good rest of your morning, and I will see some of you in office hours.